Welcome to today's class. Yesterday we discussed about convolution neural network. When you come to the recurrent neural network, the reason for this recurrent neural network is if you take ANN or CNN, it will work with a fixed dimension data. So we have to give a data with a fixed dimension. But there are some cases in the generation of text. You see, when you type in the Google, what is the weather you will type, and you will have some predictions below. In the email also, if you type something, the text will be automatically generated. And moreover, the input is not fixed here. So we'll keep on type, and the input is also varies. So in those cases, this recurrent neural network will be helpful. So that's what I have shown here. With continuously generated text, the size of the input dynamically changes neural networks. Okay, the size of the input dynamically changes. In those cases, we can use recurrent neural network. Okay, now we come into the look into this picture. This is the picture of the brain. We know neural network mimics the human brain. So the human brains have cerebrum. This whole thing is called cerebrum, cerebellum, and then brainstem. So the cerebrum has 4 lobes: frontal lobe, parietal lobe, and temporal lobe, and occipital lobe. So this each and every lobe has some features. Okay, if you take the temporal lobe, the memory of this temporal lobe is long-time memory. Okay, so the long-time memory. For long-term memory, this part of the brain is used, that is temporal lobe. Okay, so if you take ANN, artificial neural network, it is like a temporal lobe because the weightage there, once you are trained the model, the weightage will be there for a long time. It will not change in a short time. So that's why we can relate this temporal lobe to the artificial neural network. So that we have discussed yesterday. When you come to the occipital lobe, it deals with the images. Okay, it's like a vision. Okay, this is mainly this part of the brain is for the vision. Okay, so we are seeing everything as in the form of images. So similarly, we can relate this to the computer vision. Occipital lobe, we can relate to the computer vision that we are going to discuss tomorrow. Okay, and another part of the brain is called frontal lobe. This part of brain is responsible for short-term memory. Okay, so recurrent neural network, we can relate recurrent neural network with this frontal lobe because recurrent neural network has short-term memory in the neural network. So this parietal lobe is for spacious geometric dimensions like that. We don't have a neural network for this one. Okay, so now with this we can have all the areas were covered by the neural networks. You can have the computer vision, and you can have a normal a artificial neural network, and we can have a recurrent neural network in the form of frontal lobe. So this is the idea behind the generation of this algorithm. Okay, now we come to the definition of RNN, how this RNN will work and what is its structure, everything. The idea behind RNN is the neurons have some sort of short-term memory, okay, providing them with possibility to remember, which was in this neuron just previously. So what is the idea behind the RNN is, in some cases, we need the short-term memory. For example, in the Google Translator and all, if you type something, for example, when you read any document, when you are reading any story, you cannot understand the story by reading the 5th line or 6th line, okay, alone. We have to read from the beginning. We have to read the story, okay, and then you have to remember what you read on the first line. Then only you can able to understand the 5th line and 6th line. So we need some sort of memory to read the document, right? So otherwise we cannot able to understand what is there in the 5th or 6th line or in the 10th line or in the 100th page or 50th page. If you know what is happening from the beginning, then you can able to relate and then you can able to understand. So in that way, for many applications, we need a short-term memory so that we can able to perform lots of applications. So how they are going to achieve this is using recurrent neural network. So let's see. We know this is the normal artificial neural network. You have input layer, hidden layer, and output layer. So we know the function of this. We discussed that yesterday. And what this RNN is, we will skews this. So this is the normal neural network. What we are going to do is we are going to squash this. Okay, we are squashing that like this. All the input layer, hidden layer, and output layer connections are there. But yes, we are squashing that, and then we are rotating. So the yellow is input, green is hidden, and red is output. And then we are tilt that. So here at the bottom you have the input, and the middle you have the hidden layer, and the top you have the output. And this is not a single circle. Behind it you have lots of neurons. Okay, it is actually we are squashing that, and then we are tilting. Okay, behind that in the three-dimensional view you have lots of neurons behind each and every circle. Okay, and then this is your normal thing. Okay, we have the input and we have the output, and this is the, but in the RNN you have the input and you have the output, plus you have a, okay, how the memory is achieved is with the help of this feedback. So here you have the HT, that is feedback into the hidden layer. Okay, so this feedback loop performs as a short-term memory in the recurrent neural network. That is the basic, again, the basic idea behind that. Okay, this loop is called temporal loop. This loop is called temporal loop. Hidden layer not only gives the output, not only gives the output, it also gives the feedback to itself in the recurrent neural network. Keep that in mind. So when you expand this, okay, so this is the block diagram. When you expand this or unroll it, you will have a thing like this. Okay, behind each and every block you have lots of neurons. It's not a single value. You have a array of values or vector. Okay, keep that in mind. And then when you unroll it, it will be like this. We have x0, x1, x2, x3, x up to xt, and you have corresponding outputs. And okay, so and then you have the input, the weightage value. You can see the weightage value here. WXH is a weightage value between hidden layer and the input layer, and weightage WHY is the weightage between the hidden layer and the output. And you have one more weightage that is between the hidden layers. So this is the hidden layer. Between the hidden layers itself, you have another weightage that is WHS. So now we are unrolling it, and you can see the inputs and outputs of this recurrent neural network. So this is the thing. So just we are unrolling it, and then we can able to see the connection of recurrent neural network. So actually it is like this. So when you unroll it, you have lots of input and hidden layers, and then you have lots of output. It's not that single block. It's a vector of input value, vector of hidden layers, and vector of output values. But it will pass from this feedback here is pass from one hidden layer to another hidden layer, another hidden layer. Like that it will go. And then you have the corresponding output also. Okay. So try to imagine this. So this is the architecture of the recurrent neural network. So this performs the short-term memory. So the hidden layer feedback is there now. This performs the short-term memory. That will be very useful in many applications. One of the applications is you can see this application. We are sending an image into the model. This is the image. So the dog is running over the bar, but we are not giving any label to that. We are just passing the image, and we are applying the CNN to this image. The CNN will identify this is a dog, and the colors, everything is identified. And then it passes that information to the RNN. RNN will identify this is the RNN will give this text. What it gives is black and white dog jumps over bar. Okay, exactly, it gives the correct information about this. So this application is one to many. We are sending a single image into the recurrent neural network. And then that recurrent neural network identifies what is that in the image, and it gives the text. Many words are there. A black and white dog jumps over the ball. So this is an example for that. And another thing is, this is also one of the applications of RNN, sentiment analysis. So many to one. We will send many commands into the neural network, many words. That means many words are there. Thanks for a great party at the weekend. We really enjoyed it. So this is the word one by one we are sending into the neural network. The neural network analyzes the text and it gives the sentiment analysis. It says positive score is 86%. Okay, that means the content that we are sending into the neural network is a positive comment. We have done one machine learning project based on the sentiment analysis using NLP. Okay, but recurrent also will do that applications. You can apply that into this recurrent neural network also. And another thing is many to many. So this is an example for Google Translator. When you apply when you give some statement on English, it will convert that into another language. So that is an example to many applications. Okay. So this is an example for that. And the problem, one of the issues is we are going to discuss the some issues in the recurrent neural network. So first one is vanishing gradient. So we know what is gradient descent. This is a gradient descent. Why we are using gradient descent is to reduce the error, or we can say to find the minimum cost function. C is the cost function, that is nothing but actual predicted output minus the actual output, the whole square. So that is the square of mean square error. Okay, so actually the gradient descent is used to find the minimum cost function. Usually the cost function is high. This is the C. Usually it will be high. It will be in any position, and then step by step we will take some actions by back propagating the result, and then it will reach the minimum value, that is the optimal value. We call that as global minimum. Okay. So first we will send all the, so this is the normal neural network. How the vanishing gradient will work is, we will send the inputs with the weightage into the hidden layer, and the hidden layer sends the data into the output layer with some weightage. Okay, all those things are connected. We have the activation functions with that. First this is called a feed forward from input to the output layer. And then there is another thing. After you have the output, it will be compared with the actual value. If there is some error, that error will be back propagated into the neural network. The neural network will adjust the weight based on the feedback, and then the error is reduced based on the adjustment of the weight. So that is the normal function that we have in the neural network. So when you come to the recurrent neural network, how it will be is, usually we pass the input here. So this is the input. First we'll send the input. That input will be this is the bunch of hidden layer will be there, bunch of input will be there, and we have the output. So we send the input and it gives the output. Okay. With that, in a recurrent neural network, there will be another output in the hidden layer. So that is called, we call that as feedback. It is passed into the another block here, and then that is passed into the another block, and then corresponding output and corresponding output. Like that, it will be propagated. Okay. So each time you have the output and you have the error function. So that error function will be feedback into this recurrent neural network. For example, in this example we take, so these are the error functions. So t minus 3, t minus 2, t minus 1, epsilon t and epsilon t plus. So these are the error based on the output. Okay, when it compared to the actual value. Okay, first the information travels through time in RNN. So we'll have one by one. Okay, we call that as timestamp, which means the information from the previous time points is used as an input for the next time. So here, this is the previous point. The the output from this one as used as an input here. We have the actual input plus we have the input from the previous timestamp. So we will use that. So this called as short-term memory. And then we will calculate the error. So this error will be definitely feedback. Okay. For example, consider this point. This error information will be feedback into the recurrent neural network. Okay? When it feedback into the recurrent neural network, there the problem comes. Usually, when you feedback, based on this only the weightage value will be changed. So the weightage value is very important for learning. Am I right? So when you have initially the weight is high, and then gradually it becomes very less and less and less. Okay, when you multiply a small value, okay, with the weightage, so the wrec here is no, so that is the feedback weight. That will be very small when it moves backward, okay, because it has to travel to all the neural net to all the timestamp behind that. So obviously weightage value, when you multiply a small value with any value, the value will become less, further it will reduce. Okay, so what will happen when it reduces further is, so this is the representation of the wrec value will reduce further after passing every timestamp. It reduces very fast. So this is the equation behind it. Okay, so just we will understand by the picture. Okay, so it decreases very fast. So when it decreases very fast, it becomes very difficult for the neurons to learn. Okay, so when the weightage is high, the learning will be more. When the weightage is very less, the neuron finds it difficult to learn. Okay, so that is called vanishing gradient. So here you have the wrec is high, and this neurons learns very fast. And then this is very less, this is very less, this is very less. When it goes to 1000 or 50,000 or 50 or 60 timestamps like this, means at the end the neurons is finds very difficult to update the weightage value. Okay. So this is called vanishing gradient. Okay, are you able to understand? So initially the error will be feedback. Okay, feedback into the recurrent neural network, but this value, wrec value, will keep on decreasing. So when you have a 1000 timestamps or 60 timestamps like that, the vanishing the gradient will keep on vanishing. When you multiply a number with a small value, the weightage will be very, the output will be very, very less. Okay, and then the neurons finds it difficult to understand the input value. So this is the problem in the recurrent neural network. Okay. Similarly, if the wrec is high, so what we can do is, okay, so we should avoid the we should not make this wrec to be very low. So we have to increase. When you increase the wrec, means it causes another problem. What that problem is? Exploding gradient. Okay, when you multiply a value with which is greater than 1, and then again the value will be exploded high. Okay, that also gives us wrong learning. Okay, you should not have high gradient value, and you should not have less. You should not make it to vanish, or to counter attack. If you increase more, then that is also a problem. So that's what we can come to the conclusion. The problem here is, when wrec is very small, you have a vanishing gradient. If wrec, that is the weightage, that is feedback from this one, is large, we have a exploding gradient problem. So this is the equations for that. So to avoid this, we have solutions. Many solutions we have. By the exploding gradient, we will truncate back propagations. So we will not have a back propagation to all the neurons. We will truncate some of the neurons. And then penalties. When the gradient is high, we will reduce the value by giving the penalties. And gradient clipping, we can fix on threshold, and then we can able to avoid that high value of wrec. And another thing is vanishing gradient. So vanishing gradient, I told, it will keep on when you moving means the values is reducing very fast, because it is when you multiply a small value with the any other value, the output will be very small again. So weight initialization we can do, and echo state networks we have, and another thing is called long short term memory networks. So this is called LSTM method. So this is the most popular one that we are going to use in our algorithm, that is called LSTM, long short term memory networks. So how this long short term memory network works is, we will make this WREC equal to 1. So when it is very less, it is vanishing. When it is greater than 1, it is exploding. So what we have come to the conclusion is, when you make this equal to 1, okay, when you make this WREC equal to 1, then we can avoid the vanishing as well as exploding. So how we can do that? Okay, so this is the standard RNN cell. Without LSTM, the RNN looks like that. So we have the input here, hidden layer, and this hidden layer gives the output, well as it is pass that information to the another timestamp. Okay, and again these two are combined, and then tan h value -1 to +1, and then again it is passed like that. So this is the general standard RNN network. Okay, without LSD. Okay, this will provide the feedback and memory. But we have a problem that is called vanishing gradient or exploding gradient. To avoid that, we are coming into this LSTM. So this LSTM actually modifies this RNN cell like this. Okay, so it looks like some circuit here. Okay, so actually what this does is, it provides that solution. It makes the WREC equal to 1. It will avoid the vanishing gradient as well as the exploding gradient. Okay, so we have some cells here. So this is sigmoid cells. We have 3 sigmoid cells, and we have some walls. This cross circle is called walls. We have 3 walls, and tan H is there. It is already there in the standard RNN. Okay, and this is the thing. You have the input and the output, and this is the output from the hidden layer to another layer. Okay, let's see how this works. To solve the problem, here we are making WREC equal to 1. Okay, the top line is there, no? This top line is actually called as memory line. Okay, this top line has the value WREC equal to 1. When you not disturb this line, so this line is nothing but a vector. This is a vector, bunch of lines, not a single line, bunch of line. This will make or rec equal to 1. Okay, that is nothing but recurring weight equal to 1, and it pass into this to the next stamp, next step with that. Okay, so this is the memory line, and we have something here. So we have this one thing is here, and then second block is the third block here. So we will see what is this function. A straight pipeline at the top is called memory line, that is responsible for WREC equal to 1. When you see it in detail, we have CT. So CT stands for input from the memory cell in time t. Okay, so before that you have this is the time t. This is time t minus 1. Okay, and this is the input to time t. Okay, the memory cell, and x of t is the input in time t. Okay, xt, and then ht minus 1 is the output of xt minus 1, and it is the input for x of t. Okay, so we have taken the particular block and we are going to see. This is the output. This is the x of t is the input, and ht is the output of this timestamp, and we have the output of this hidden layer. Okay, to the output layer. Okay, so what we can understand is, each block here has 3 inputs. One is xt, another one is xt minus 1, another one is ct minus 1, and we have 2 outputs. That 2 output is ct, ht. Okay, so this is to the another block, and this is to the output. This line, this black line is called vector transfer. That means a group of numbers. and this represents concatenate. Concatenate means these two are joined together. Okay, parallelly it is joined, not mixed, it is joined. And this is copy. The same values has been passed into two areas. Here you can say it is copy. The same value is passed to the next block as well as to the output layer. And point-wise operation. So this is the point-wise operation. It is called wall. So this is the thing that we are going to discuss. And this is called neural network layer. So you have multiple layers. So that's why the neural network is mentioned. It's not a single sigmoid value. You have multiple values behind it. So it's very difficult to imagine, but we try to understand what is happening inside the LSTM, how the LSTM learns. So that's what we are focusing on. So there are four main operations in LSTM shell. So this is your LSTM shell. We have four main operations. The first one is forget. The second one is store. Third one is update. And fourth one is output. Let's look at this. We have first wall, second wall, and third wall. Okay. The first wall is called forget wall. The second wall is called memory wall. And the third wall is called output wall. Okay. Now we come into this. We have the forget, memory for storing. And third one is update. We have combined it together this one, and the fourth one is output. Let's see that. So what this forget wall does is forgets the irrelevant parts of the previous state by passing the previous state to one of the sigmoid function. For example, so this is the default weightage function that I said, w rate equal to 1, the previous one. So C of t is the thing, okay? And this has been passed through this wall. Okay, when you make this to 0 or 1, sigmoid is nothing but 0 or 1. If you make this wall open and close, when you open this value will be passed here. When you close it, this value will be sent. So where we can apply this is, if we have if you needed a good value, for example, if your statement is there, is a good boy. Okay, so there, if you are storing that E or whatever it is related to the statement, okay, the correct statement. If you have the correct statement, we can pass. If you have the wrong prediction, okay, it is not needed for the prediction, means you can stop it by sending the new values from the input. Okay, that means it forgets the irrelevant parts of the previous state. So it should not carry all the values from the previous state to the next state. Okay, only when it is needed, relevant parts are coming, means we can keep. Otherwise, we can we can cut this input, and then we can give our input from the input as well as from the ht minus 1. Store represents part of the old information is relevant and stores it into the cell. Okay, if you think this part is very important when you discuss about some person, when you talk about election, means election is the term that you will use, isn't it, throughout the article. So like that, if the old information is relevant, cell will store that. That's why it is called store, or it is a memory wall. Okay, it is stored in this area. Okay, so we are sending that information, and through that wall and through this one, you can able to pass to this area, and then you can pass through this output also. Okay, so this is the storing area. And another thing is, apart from hidden state, LSTM also maintains a separate C of t. So that's what I told. So we no need anything here. So when you don't have any irrelevant informations or nothing related information in the output, means we can have a separate cell from this point to this point. This is called updated value by the gate operations. Okay, so this is another type of passing the information. And the final one is output gate. Output gate controls the information that has been sent to the next cell. Okay, from this cell to this cell, if you want, you can send this to the next block, and you can send that to the working by automatically. So what we are going to do is we are just going to pass the information. The recurrent neural network learns like this. Okay, we can study that from the understand from this example. So for example, so this is the line that we are typing. Okay, so first what we are doing is we are typing W. Okay. When you type W, what will happen is there will be some predictions behind it. So these are the timestamps. Okay, 1, 2, 3, 4, 5. Like that, you have the predictions here. So the dark red is the correct prediction. Okay, that is a the algorithm thought it is a relevant data. Okay, and then that white blocks the algorithm thoughts it's not relevant, but it keeps on guessing some values. Okay, okay. So when you type W, the algorithm understand next value will be W. So that's why it giving dot. When you type W again, the algorithm again guesses it is okay. And when you type again, the algorithm understand this is WW dot, and then it gives the suggestion dot, and then the algorithm guesses a value B. So how the algorithm guesses is from the previous memory like that. Okay, so it keeps the relevant data and it forgets the unrelevant data also. So it suggests you B, but that is not the correct one. We are typing another one Y. Okay, now the algorithm gets understand. Oh, our guess is wrong. So it will ignore that relevant data or forgets that relevant data. Okay, and then again it guesses something that is A, but it's not dark red. It is small, slight red only. Okay, it's guessing, and then that is also not matching. Again, this will not keep that in the memory, and then this also be ignored, and then again some other letter. So that is also not matching. Some other letter that is also not matching. So like that, it is guessing one by one. But why net NE? It's not able to guess what we are typing. And then next we are type the W. So when you type this one, why net new algorithm learns from the thing, English knowledge, it says it thought next letter must be yes, maybe news. Okay, so that's why it give correct yes, dark red is there. And then once you've done that, the algorithm again predicts a dot, and then if it is right, the algorithm keeps the value. And the next thing, the algorithm uh, identify www dot, definitely it will be a .com or .in. I don't know. So when you type C, it guesses C, but it is not. And then type C, it understands next will be 0 and next will be 1 like that. So in that way, it will the recurrent neural will work. So in that for that only we have that forgot memory and then update and storing. Okay. So the next thing you can see when you are typing E, the algorithm doesn't have any clue what the word that you are going to type. But when you type he, it's guessing something. When you type N, it understands it may be English, so it's predicting something G, and then it becomes very confident. This must be H. So like that, the algorithm works. So this is the working of recurrent neural network with LSTM. Okay, so that's all about the intuition of recurrent neural network. So this might be a long intuition. So we will discuss now. If you have any discussion point, then we can discuss about this recurrent neural network. Then we move on to the implementation. So this is one prediction, text generation prediction. Anything want to discuss? I'm waiting for the response. Shall we move on to implementation? So what example that we are going to analysis are going to do using RNNs? We are going to do a stock prediction. First step is importing the libraries. Before that, I will explain the data set. When you go on the top, we have four columns are there. First one is date. Another one is open, high, low, close volume. So this is the date, and you know that stock market works only on the weekdays, right? So we have a 3, 4, 5, 6, 4 days here, and then 7, 8 is holiday, and you have 9, 10, 11, 12, 13, so 5 days a week. And this is the open point of the stock. And this is the high value that is reached on the day, and this is the low value that is reached on the day, and this is the closing point of the stock, Google stock, and finally how many volumes, okay, is the stock stand. So what you're going to do is we are going to predict the stock price for the Google. Okay, so that is the basic idea behind this. We are going to predict, and using what value we are going to predict is based on the open value. Okay, open means at the morning when the stock market opens, what is the of the stock. So based on this, we are going to predict a Google stock predictions for a day. Okay, we are going to create a model for that. When you see this, view this in the chart, you can see the graph. So this is the stock of open. Okay, when the market opens, this is the stock point. Okay, this is the actual value. It is not a prediction. This is the actual value. We are going to train the model with this data, and we are going to test it. Okay, after that, what we are going to do is we need to test. So the test file is another Excel file. It contains 20 data. That means 20 days. Okay, so this value is an unknown value for the model. So we are going to train the model with that data, and we are going to test the model with this value. And when you test, you will have some prediction, right? That prediction and the test value prediction, based on that, we are going to find the accuracy of the model. Okay, how the model matches. Okay, when you see this graph, not the graph that you're interested, okay, select it. You can see this is the model for the test. So after applying this test value, we have some predicted value. And when you compare these two, if the model performs well, then we can say the model is working good. So let's see how it works. Okay. So this is the idea behind the project. Okay. Now the library functions, as usual, NumPy, Matplotlib, Pipe, and then Pandas. So these are the library functions, common library functions that we used for the machine learning. And NumPy is for dealing with the array, and Matplotlib for plotting the plots, and Pandas for accessing the CSV. Right. So when you run it, so before that we have to connect with the server. It's taking some time, and I already told that change the runtime to GPU. When you are using neural network, use the GPU, but the GPU is limited. After that, importing the training set. We don't have time, so I'm just copy and pasting. So these are already we know that data set train is the variable. PD read CSV is the function to read the file. So what is the file name is Google stock price train.csv. And then training set is we are going to take what is the value that you are taking using this ilog. I already taught this ilog once. What this ilog says, the first column represents all the rows. This determines the column. Okay, this is the upper limit. 2 is the upper limit of the column. Okay, but we should not include that. The algorithm will not see the 2. Okay, it will see the values between 1 and 2. It will take the lower limit, but it will not take the upper limit. So that means it will take only the first column. Let's see how it is. Before that, we will upload the data. Just copy it. So this is the path. Copy path and paste it over here and then run. Okay. Now let's see what this data set contains. Initially, there's all the 5 columns: date, open, high, low, close, volume. We are interested in the open column. So open column is what is the number of the open column is? First column is 0, that is date. The second column is 1. This is the 2. High is the 2 column. The low number column is 3, 4, 5, like that. The first column is open. So we are interested only in the open. So that's why I have given 1, 2, 2. So 1 to 2 means between 1 and 2, all the columns will be passed into this training set. So between 1 and 2, you will have only 1 column. That is the lower limit. The upper limit is 2. We should not take that. 2 minus 1 is already 1. So that means we are taking this column alone. If you give 1 to 3 and run it, okay, and here also if you run it, and if you see the training set, you will have 2 columns. So what is that column means? It takes the open as well as high. So I don't want high, I need only open. I make this 2. Okay, so that's the function of this. ilog will not take the upper limit. Minus 1 only it will take. So and then training set, when I run that, you have only 1 column. That column is nothing but this open column. And the next part is feature scaling. So why we need to do the feature scaling? Here the values is 25, 793 like that. So there will be a variation in this values. So what we are trying, because it is of different years, okay. So last 5 years the value will be changed drastically. So then for neural network, if you give high values, it takes more time to processing. So the scaling will be better. We do the scaling in the CNN also. For image also, for pixel value, we do the scaling. Similarly, here also we are going to do the scaling to normalize the value. So already told there are two types of scaling. One is standard scaling, another one is normalization. Okay. So normalization is nothing but min-max scalar. So I am going to apply that. The range will be 0 to 1. So this is from the sklearn. Okay. And what I'm going to do is I'm going to fit means I'm going to train all the values of the training set, and then I'm going to train all the values in the training set, apply the transformation into that, and then the result will be stored in the training set scale. So when you run this one, you can see all the values now will be in between 0 to 1. So before that we can see it is 325 and the final value is 782 like that. 793 is in between that. So there is different values there. But after applying the scaling, all the values is between 0 to, so that is the use of feature scaling. So we have already learned that. So when you have a sigmoid function at the output network, normalization scaling is preferred. So usually we are using sigmoid function at the output of the neural network. So for a neural network, normalization scaling is preferred instead of standard scalar. And then recurrent neural network, you will have time steps. Am I right? So xt minus 1, xt minus 2, like that you have time steps. So now we are going to create a data structure with 60 time steps and one output. What does it mean is it is going to take 60 values from the data set and then it is going to predict. So the prediction of the output is based on 60 previous values. We call that as time steps. It's very interesting one. We will try to understand. Okay, take this code. So first line is we are creating two lists. Okay, one is X train, another one is Y train, empty. And then we are creating a for loop from the range 60 to 1258. So what is this 1258? Okay, when you see the shape of the X train, okay, I'm giving the, okay, so it's not because I have to use here. When you go for the shape of the, so this is the transformed value, but the number of values will be, the size is not varying, only the function. So how many values are in the training set? 1258 and all in the same column, single column. Okay, so that is the shape. So I am taking the upper limit as 1258, the range, and the lower limit as 60. Why I am going to take 60 is I am going to consider 60 time steps. So 60 days, that means 3 months. So each month has 20 days. So 3 months is 60 days. I'm going to take 60 values from the data set, and then based on that, I'm going to predict one. Okay. So that is the idea. So why 60 time steps? Can we take 20? Can we take 30? Can we take 40? Can we take 80? Yeah, you can take. Okay. So it is our wish only. If we have to check whether it is working well for 20, the accuracy, if the accuracy is good, we can go for 20. If it's not good, they can just increase the time state and you can find out what is the accuracy. Okay, so like that we can do this with trial and error. Okay, so that is the number of time state. So that's the lower limit is 60 and the upper limit is 1258. And then the next is xtrain dot append. Append means is going to join the values. The training set scaled. Okay, so this is the transformed trained value, the xtrain value. Okay, starts from I minus 60 to I comma 0. So what this value represent is I minus 60 means I starts from 60. I already told why 60 means 60 times. So when it reaches the value 60, okay, I'm not using the GPU. Okay, so 60 minus 60 is 0. And then here the upper limit is 60. So all the 60 values from a beginning to the 60 values, okay, has been. So that means we initially we start the Python will start from 0 to 59. So for us it is 60. It will actually from the data set, if you see 0 to 59 rows are taken in a single column. We call in the zeroth column. Okay, so in the all in the 1258 data, we are taking the first 60 values in the data set and you are storing that in a column. And Y train append. Okay, what that means is the 60th value. Okay, 0 to 59 is the values that is taken for training. Okay, the output of this value will be the 60th value. Okay, I will tell you what is that. Okay, so we take that value and store that in the other column, that is in the Y train. Okay, so like that all the values will be stored and then we are converting that into array. So when we look at into the first 60 values, it is taking predict one output. So that's why it is called 60 time step and one output. Okay, the prediction, the one output is based on 60 time step. So that means in this data set we have 1200 something data is there. That means 1258 data. So we will start with 60 because the previous values, based on the previous values only, the next output will be there. So the first 60 value we take as a for train, and the next value from the data set is taken as Y train because that is the output for the first 60 steps. For the next 60 step is we come one day later, the next day, and then again the next 60 days we take. Okay, and the 61st date will be your Y train for that 60 days. Similarly, we shifted one more values. That's what we are seeing in the, we see that in the X train. So this is the first 60 value. Okay, and we have a Y train as all this from the data set. We are not predicting here. We are not creating the model. From the data set, how we are separating X train and Y train is first 60 values. That means 60 days we are taken. The next value will be your Y train. Okay, and then that is your actual stock price. And then we are shifting down one day. So that means we are starting from 0.07 in the next prediction. Okay, the next state will be start from this state. Okay, up to 60 values. Okay, and that prediction, the next to this 0.862 values in the data set is 0.084. And then again we are shifting down once. So we are starting from this point. Okay, and then we are including this value, okay, in the next, because we are shifting one by one. And the next year again the 60 values, 60 days values we are taking from the data set. The next value will be your Y train. So that is nothing but 0.0744. So like that we are separating the X train and Y train. After that we are reshaping that. Why we are reshaping that means for RNN we have to give the data in the 3-dimensional. Okay, one dimension is total data set of X train, and another one is number of timestamp. This number of timestamp is trial and error. We can fix 20, 30, 60, 80 also we can take, and we can see the performance. And this one is the indicator value. When you have 2 or more stocks, then this will be increased. Otherwise, we can make this as 11861. So that means this data in the right shape for training the RNN. The next step is we are building and training the RNN. For this, the layers that is required is sequential, dense, LSTM, and dropout. So these are the layers that is needed for building the RNN value. Okay, the first step is initializing the RNN. We are taking the sequential model. That means from the input layer to the output layer, feed forward. Okay, and the variable is regressor. And then we are adding the LSTM layer. So that is the first layer. LSTM means the number of unit here is 50, and the return sequence is, that means what the return sequence says is we have more than one LSTM layers. If the return sequence is false, then you have the single LSTM layer. Okay, then input shape. Input shape I already told it is a 3-dimensional one, and 119861. So xtrain.shape1 represents the 6 time step. So it is 60, 1. The total number of data set, the LSTM layer taken by default. Okay, it knows that. And then dropout. So this is the one thing you have to learn. Dropout means we are not connecting all the 50 units with all other neurons. So we are dropping 20% of the neuron. That means 20% of the neuron randomly we are selected and we are not connecting that, we are dropping that. Okay, why we are doing that is to avoid the overfitting. Okay, so that is the dropout function. Overfitting means overtraining. Once the network is overtrained, cannot predict better. Okay, so always there should be some non-linearity in the predictions because the value may be high, the value may be low. If it is overfit means it will not follow the changes in the input. Okay, so that's why we are doing some dropout. Okay, 20% means out of 50, 20% means 10 neurons we are dropping out. Randomly we are selecting at each layer. Okay, and this is the another thing. And the second layer is second LSTM means the same thing. Only thing is we are not mentioning the inputs here because it is the hidden layer, the next to the input layer. So it no need to mention. Again, I'm return sequence is true. That means we have one more LSTM layer. That is the third LSTM layer of the same units 50 and drop. So we can have a different units for that also. And the fourth LSTM layer is unit 50, and we are not mentioning the return sequence equal to 2. The reason is we don't have the fifth LSTM layer, so we are stopping here. So that's why I'm not mentioning return sequence here. After finishing the building of LSTM layer or recurrent layer, then the final is the output layer. The output layer is only one output. Okay, only one neuron because we are going to predict a value of the stock. Okay, and then compiling the neural network. So before training the neural network, we need to compile with an optimizer and the mean square error to calculate the mean square error and to optimize the error. Okay, and finally recursor.fit it trains the model with X train and Y train. We know the X train is the 60 days. Okay, X train has 1,190 data, but it will take 60 at a time. Okay, and then you have the Y train for that, like that. Okay, so already we have mentioned that. So here what we are going to do is we are going to take all the X train and Y train to train the model, and epochs means 100 times that you are going to train the old X train as well as the Y train data. And the batch here is 32. Okay, that means batch of 32 will be sent at a time. Okay, so that means first epoch is 1 to 100, so only 38 times the first batch, second batch, third batch, like that 38 batches has been sending into that, and the loss is predicted. Similarly, for the second time, third time, like that, 100 times I've executed already. Okay, so it will take some time. You can see the loss is gradually reducing, and then making the prediction and visualizing the result. So the model is trained with the X value as well as Y value. Now we are going to see the prediction. We are going to evaluate and we are going to see how our model is work. So for that we have a CSV file called stock price test. In the stock price test, you have only 20 values. Okay, in the stock price you have only 20 values. That is 2017 January month values only. So we have only 20 entries. But for prediction, we have taken 60 times state. 60 means we need 60 values. Okay, so for that, what we need to do is we need to take the remaining values from the training set. Okay, the training set as the values from 2012 to 2016 actually. Okay, so the previous values are there in the training set. So the first 20 values it is taking from the test, and the remaining values it is taking from the training. For that only this line does. So for that only we are concatenating the data set train as well as data set test, and we are keeping that in a single column vertical, and then we are comparing the length data set total means the total number of data set total and the total number of data set test minus 60 value in the rows. Okay, and dot values. So when you what it will do is to predict this value. Okay, so this is your actual value. Okay, so to so these values depends on the previous 60 values. So that is what we are making. So timestamp is 60 means before 60 days, based on the 60 days only this value is there. Okay, so this value is based on this value as well as the previous 59 values that is in the train state. So like that, it will have one by one. Okay, okay, and then we are reshaping that, and again we are applying the transform into it. So that is what we have there at the input. When you give input dot shape, inputs actually inputs dot shape, we have 80 comma 1. Okay, we have 80 comma. So what does this means? So we have the total minus data set minus 60. Okay, so we have 80. Okay, so we are going to create a test sequence. So that's why 60 to 80. So we start from 60 to 80. One by one, we are going to predict. So like I said, one by one, we are going to predict. 20 values only we are going to predict. Okay, we have so we have add this, and we are getting this. And so for January 1, January 2, January 3 of the test, we are seeing one by one, and we are saving that in the X test. Okay, so there is nothing but this value. Okay, so 161 is this one, this one, this one. All these 20 values will be there in the X test. Okay, when you have the X test dot shape, you can see that. So it is 20. Okay, it is 20. We'll append one by one. So first value and the next 60 value. Like that, we have the shape. So we are interested only in the X test for predicting, but for prediction we need 60 values. No, so that 60 value will be taken from this. Okay, so that's what this I equal to 0. So when I equal to 60, 0, comma 60. Okay, 12 will be there, and I equal to 61. Then you have 1 comma 61. So that value will be stored. So like that, you will have the array. So this array is 20 by 60. So try to imagine that. And then we are again reshaping for a model. So we need a total tester, and then 60 is the time step. This is the total 20, and this is the 60, and this is the 1. Okay, when you reshape that, you are getting the three-dimensional. And then we are applying that X test into the regressor, and we are taking the inverse transform, and we are getting that. And finally, visualizing the result, we are going to get the real Google stock price. Okay, that is from the predicting. So this is the real Google stock price, the real stock price. So we have that, and this is the predicted stock. When you run this, you will have a prediction. So what you have to understand is this is the real Google stock price, and this is the predicted one. We have some peaks in the real time because there will be many factors. It's not that some news, some election, some whatever it is, it may just increase to the peak and then coming down. But the predicted value, you can see here it's increased, here is also increase, and here it is somewhat constant, here also somewhat constant, here it is increased, and here also it is increased, and here it is decreased, and it is decreased. So it is not following the peak, but it is following the projection of the real value, real stock value. So in that way, we can say this model is working properly.